Hey stats fans, welcome to another deep dive. Today we're going to be looking at factorial designs.
Oh, yeah, those are really cool.
Yeah, and I think it's something that a lot of statistics students, they might be familiar with testing one factor at a time,
Right.
but this is kind of a different way to approach it.
Yeah, definitely. In a factorial design, we can test multiple factors simultaneously
Okay, so at the same time.
at the same time.
Definitely.
And this allows us to see the interaction effects between these different factors.
Interactions, that's interesting. I've heard of those, but how's that different from just testing one thing at a time?
So imagine you're trying to bake the perfect cookie right.
Okay, I like where this is going.
And you're changing the sugar type. Maybe you're using brown sugar, white sugar, or something else.
Oh,
And you're also playing around with the temperature, baking it at different temperatures.
makes sense.
Now, if you were to just change one factor at a time, you might say, okay, well, this type of sugar always makes a chewier cookie. But with a factorial design, you might find that the effect of the sugar actually depends on the temperature that you bake it at.
Hmm.
So maybe that sugar only makes a chewier cookie at a lower temperature.
Gotcha.
But at a higher temperature, it actually makes a crispier cookie.
So it's not just the sugar itself, it's how it interacts with the heat.
Exactly. Exactly. And that's something you would completely miss if you were just doing a one factor at a time experiment.
So is that the main benefit of using factorial designs then?
It's one of the main benefits, yeah, because you get a more complete picture. You're not just looking at each factor in isolation.
Okay.
You're seeing how they work together.
That makes a lot of sense.
Mm-hmm.
So would that then lead to us having to run a lot more experiments because we're testing more things at the same time?
You might think so,
Yeah.
but factorial designs are actually more efficient, believe it or not.
Okay.
So you can get more information with fewer experimental runs.
Now that you mention it, that was one of the things that always confused me about factorial designs. Can you give me like a real-world example of how that works?
Sure. One of our sources talks about a case study from SKF, a bearing manufacturer.
Yeah.
And these engineers, they were trying to figure out if a new cage design would make the bearings last longer.
Okay, longer-lasting bearings. Who doesn't want that?
Exactly. So they were originally going to run 8 tests comparing the new cage with the old cage design.
That sounds like a good start, yeah.
Right.
Yeah.
But a statistician named Krister Hellstrand, he came in and said, you know what? We can actually test 2 more factors without increasing the number of experiments.
Wait, really? How is that even possible?
So what he did was he used something called a 2 by 2 by 2 factorial design, which allowed them to test 3 factors simultaneously.
Oh, okay, a 2 by 2 by 2.
Yep. And those factors were the cage design, the heat treatment of the bearing, and something called the outer ring oscillation, which basically describes how the outer part of the bearing fits into the housing.
Okay, so they're getting triple the information for the same amount of work.
Exactly. And you know what they found? They found that the cage design itself didn't really matter that much.
Huh.
But when they changed the heat treatment and the outer ring oscillation together, they saw a 5-fold increase in the bearing life.
Wow.
Yeah.
Talk about a game changer. So the cage didn't matter as much. It was more about how these other 2 factors interacted with each other.
Exactly, yeah. So it wasn't just the individual factors that were important, it was the combination.
So how do they do that then? Do they just like randomly change all the factors all at once and then just like see what happens?
Well, randomization is important to make sure you don't introduce bias into the experiment, but you don't just randomly change things.
Okay.
There's a system to it.
Okay.
So what you do is you set the factors to specific values based on what's called a design matrix.
Okay, so there's a method to the madness.
Yeah.
I like it. So are there different types of these factorial designs then?
Yeah, absolutely. The simplest one is called a 2-level factorial design, and that's the one they used in that bearing example.
So you just have like high and low settings for each factor?
Exactly. Yeah, you got it. So you test each factor at a high level and a low level, and that allows you to look at the main effects of each factor.
Okay.
And also, it helps you see how they interact.
Okay, that makes sense. So are there other types then?
Yeah, you can have what's called general factorial designs, where you can have more than 2 levels for each factor.
Okay.
So you get a more detailed look at things. And then you also have fractional factorial designs, which are helpful when you have a lot of factors to test.
Okay, now I'm starting to see why people get kind of freaked out when they hear about these factorial designs.
Yeah, it can be a little overwhelming at first.
Yeah, it can be a lot. But it sounds like they're super valuable and worth learning about.
Oh, absolutely. As a statistics student, I think it's essential, to really understand how to design effective experiments.
Okay, so we've learned that factorial designs are more efficient. They can reveal these hidden interactions, and they're different types depending on what we're trying to do.
Exactly.
But before we jump into all the different types and how to choose them, let's talk a little bit about how to analyze the data that comes out of these experiments. We'll be right back. Welcome back, everyone. So we've got a good handle on what factorial designs are and why they're so useful. But now let's get into the nitty-gritty. How do we actually analyze the data?
Right, yeah. That's where we really dig into those insights, uncover what those experiments are telling
This
us.
is the part where I usually start to sweat a little bit.
I know a lot of people feel that way, but honestly, it's not as scary as it seems.
Okay, that's good to hear.
Yeah, and we've got some really powerful tools to help us, like ANOVA and regression analysis.
Okay, I remember those names from stats class. Could you give us a little refresher?
Sure, so ANOVA stands for analysis of variance.
Right, ANOVA.
And it's basically a test that helps us figure out if there is a significant difference between the averages of different groups.
Okay, and in a factorial design, those groups would be like the different combinations of factor levels, right?
Exactly. So, like in our cookie example, you'd have a group for each combination of sugar type and temperature.
Okay, so it's telling us if changing those factors actually makes a real difference in like the texture of the cookie or whatever we're measuring.
Exactly. Now, regression analysis kind of takes it a step further.
Oh, okay, how so?
Well, it helps us understand the actual relationship between those factors and whatever we're measuring.
Oh, interesting.
So we can build like a mathematical model that can actually predict the outcome based on the different factor levels.
So ANOVA tells us if there's a difference, and then regression helps us see what that relationship looks like.
You got it. And both of these tools can help us understand those interaction effects that we were talking about.
Okay, good, because those seem pretty important.
Right. So imagine our cookie experiment again. ANOVA might tell us that both temperature and sugar type have a significant effect on the cookie's texture.
Which makes sense because we're testing them both at the same time.
Right. But then we can use regression to create a model that shows us how the effect of temperature changes depending on what type of sugar we're using.
Ooh, so it's not just about each factor on its own, it's about how they work together.
Exactly. And one of our sources actually has a really good example of how we can use these tools to analyze data from a factorial experiment. It talks about this engineer who's working on a chemical filtration process.
Okay, chemical filtration process. What's he trying to do?
He wants to increase the filtration rate and use less formaldehyde.
So, like, make it faster and less toxic. Sounds challenging.
Right, it's a balancing act. So he's testing 4 different factors: temperature, pressure, formaldehyde concentration, and stirring rate.
4 factors, wow. And are these 2 level?
Yep, each factor has a high and a low setting.
Okay, so 2 by 2 by 2 by 2. That's a lot of combinations.
16, to be exact.
16. Okay, so he runs all those experiments, gets his data, and then plugs it into ANOVA.
Exactly. And the ANOVA results show him the main effect of each of those factors.
Okay, what did he find?
So, like, increasing the temperature led to a higher filtration rate, which makes sense, right?
Yeah, that's kind of what you'd expect.
But then increasing the formaldehyde concentration actually decreased the filtration rate.
Okay, that makes sense too. So he's seeing those individual effects.
Right. But then here's the cool part. He found some really significant interaction effects.
Ah, so there's more to the story.
Way more. So, for example, there was a really strong interaction between temperature and the formaldehyde concentration. Increasing the temperature actually had a way bigger positive effect on the filtration rate when the formaldehyde concentration was low.
So it wasn't just about cranking up the temperature as high as possible. It was about finding the right combination.
Exactly. This is why those one factor at a time experiments can really miss the big picture.
I'm starting to get it. So are there like visual tools that can help us see these interactions more clearly?
Yeah, there are things like interaction plots, which can be super helpful. They basically show us how the effect of one factor changes when we change the level of another factor.
So we can actually see those interactions happening.
Exactly. And that can be really powerful when you're trying to make sense of all this data.
Okay, this is making a lot more sense now.
Mhm.
So this engineer, he used those ANOVA results to figure out the most important factors and interactions, right?
Yep. And then he could actually use that information to optimize his whole filtration process.
Find that sweet spot where he gets the best filtration rate with the least amount of formaldehyde. That's pretty cool.
It is. It's a really good example of how powerful factorial designs can be when you're trying to solve real-world problems.
I'm with you. So we've talked about ANOVA and regression. They sound like great tools. But how do we actually go about choosing the right type of factorial design in the first place? I imagine that's a pretty important decision.
Oh yeah, definitely. Choosing the right design is key. And that's what we'll be talking about in the next part of our deep dive.
All right, so we've really dug into factorial designs. They're efficient, they help us uncover those hidden interactions, and they lead to more insightful experiments overall. But the big question is, how do we pick the right one for the job?
Yeah, that's a great question, and there's no easy answer. There are a few key things to keep in mind when you're choosing a factorial design.
Okay, let's hear them. What should we be thinking about?
So first off, how many factors are you trying to test?
Okay, number of factors.
If it's just a couple, like 2 or 3, you can probably handle a full factorial design. That means testing every single combination of factor levels.
Right, that makes sense. But what if we have a more complex system, like 5 or 6 factors? Things could get out of hand pretty quickly.
You're telling me? That's where fractional factorial designs come in.
Fractional factorial, okay.
They let you be a bit more strategic, test a subset of those combinations and still get good information.
So it's like a shortcut, but without sacrificing too much data.
Exactly. You're focusing on the most important information.
Okay, so number of factors, check. What else?
Think about how many levels you need for each factor.
Yeah.
If you're mainly interested in those main effects, just 2 levels, high and low, might be enough.
Right.
But if you want to really understand the relationship between a factor and your response, you might need more levels.
Okay, more levels, more detail,
Exactly. It gives you a better picture, but it also means more experiments.
more work.
Yeah.
So it's a trade-off between how much information you need and how much time and resources you have.
Exactly. And those are some of those real-world constraints we always have to think about. What else do we have to work with? What's the budget? What equipment do we have? Do we have the expertise to handle a really complex design?
Makes sense.
Sometimes it's better to start simple.
Keep it manageable.
Exactly. And it's never a bad idea to talk to a statistician, get their advice on choosing the right design.
Okay, so number of factors, number of levels, and our practical limitations. Got it. Are there any downsides to these factorial designs? They sound pretty great, but are there times when we wouldn't want to use them?
Well, like any tool, they have their limitations.
Okay, what are those?
One of the big assumptions is that the relationship between the factors and the response is linear.
Okay.
But if it's curved or nonlinear, a simple 2-level factorial design might not be enough.
So we might need a different approach. What else?
Well, they do require some careful planning. You got to make sure all your factors are controlled and randomized, no confounding variables sneaking in.
Right, keep things clean.
Exactly. And with those fractional factorial designs, remember you're only testing a subset of combinations. You might miss some of those subtle interactions.
So it's a trade-off. You gain efficiency, but you might miss some detail.
Exactly. It's like looking at a zoomed-in portion of a picture. You see the main stuff clearly, but you miss some of the background details.
Okay, that makes sense. Well, this has been a fantastic deep dive into factorial designs.
Yeah.
I feel like I have a much better understanding now.
Me too. And, these designs, they're not just theoretical. They're used everywhere. Engineering, manufacturing, medicine, even marketing.
Wow, so no matter what our listeners are interested in, understanding these designs can be a huge advantage.
For sure. It's all about understanding how those different factors work together, and that's a critical skill for anyone working with data.
Well said. So, any final words of wisdom for our listeners as we wrap things up?
Don't be afraid to embrace these designs. Move beyond that one factor at a time approach. Start thinking in terms of interactions. And remember, there's a whole world of statistical tools out there to help you unlock those insights hidden in your data.
Great advice. So listeners, get out there, start exploring, keep experimenting, and don't hesitate to ask for help along the way. That's it for this deep dive into factorial designs. We hope you enjoyed it and that you feel inspired to put this knowledge to good use in your statistical adventures.
Absolutely. Keep learning, keep asking questions, and keep pushing the boundaries of your statistical knowledge. We'll see you next time.